Today we're going to talk about groundwater hydraulics. On Tuesday we talked about hydrology, which is kind of how groundwater works, where it is, different aspects of aquifers. And today we're going to talk about steady flow or steady state, meaning what's going in is equal to what's coming out. And our learning objectives are first to first we're going to define hydraulic and aquifer.
There's such thing as a real mass balance for groundwater. What comes in, different amount comes out. Is that even possible?
Groundwater is tough, man. It is conductivity. So we're going to define hydraulic parameters, conductivity and transmissivity. You're never going to get a perfect water balance. Honestly, it's hard to get a surface water balance. Well, because of groundwater and because of evapotranspiration.
Yeah, I feel like if we had a mass balance in groundwater, it would just be a channel.
Yeah. There are ways, to get close, and you're never going to get 100% closure on your water balance. Yeah. All right, so we're going to calculate hydraulic conductivity, these parameters, and transmissivity. Okay, so calculate these parameters. Or we're going to calculate groundwater flow rates. Using these parameters. So we'll calculate flow rates using these parameters. And Darcy's equation, also the I'm not going to pronounce this, Dupuit equation. I think that might be French. Val, can you help us out?
Dupuit.
Thank you. And then we're going to apply these, not even close, to apply these equations to characterize what's known as the cone of depression around a pumped well, so where we're withdrawing water from a well, in a confined and unconfined aquifer. All right. So hydraulics, again, is referring to the kind of physics of flow rates, and how we calculate that. All right, let's
There's such thing as oppression.
cone of oppression. It's oppressive, this groundwater. Yeah, there is a cone of, I don't know what you would call it.
Like, wouldn't you consider what Cassie was talking about with Chatfield, the cone of oppression for groundwater?
Yeah, so a cone of depression, just call it cone of depression. We saw a cartoon of that. So if this is the ground surface, and here's our water table, and you put a well in there that penetrates through the water table, and you start pumping out at a certain flow rate. The cone of depression is what happens around the well. And so you would call it a lens, a groundwater lens. And that can happen we saw when we had a river, during a flood, we maybe the groundwater during base flow looks something like this. But then a flood event comes and all of a sudden water is over the floodplain. And then we start to get the water table rises and kind of, you know, fills in this way, right? And that would be kind of the opposite of a cone of depression. So that can happen during floods. That can certainly happen from a reservoir. Where you've got a big water level and it's a reservoir that's perched, and you know, the creek used to be down here, but now you've got basically a water table that looks maybe something like that. Or it might look something like that. Okay, so let's review real quick. We have the aquifer. Whoa. Aquifer properties. The first one we talked about was permeability. And that was lowercase k is equal to some coefficient times the diameter squared. And it has units of length squared. And the diameter, does anyone remember what diameter we're talking about here?
Grain size.
Grain size. So this would be the mean grain size. Sometimes it might be the median, but we'll talk about that. So if this is a soil sample, sandy, gravel, cobbly, loamy, you can measure this directly. This gets a little funky. C is a shape factor. Yeah, D50 is the median grain size. That's often what's used in soil. This says mean. But people might use those interchangeably, but they're not always the same. And then we learned about conductivity, which was not only a property of the soil or the aquifer itself, but it was a property of the fluid as well. And that's big K. This is little k. And big K is equal to little k times the specific weight of water divided by the dynamic viscosity. And then we also talked about porosity, Eta, which is Hurricane Eta flying over Florida right now, about to hit my parents in Port Orange. I think, I don't know if it's a tropical storm or what, but anyway, so that's the volume of water over the volume of your, we'll just say total of your sample. So I don't think it's that big of a storm. My mom hasn't been texting me or anything, so I think it's okay. Unless she hasn't been texting me because all the cell phone towers have blown out. I think it's okay. All right. No, I think she would have. I don't know. There's a lot going on, so maybe you can like ignore the fact that it's almost December and there's a hurricane barreling down on you. All right. And then we introduced Darcy's law, which says that the discharge in an aquifer is equal to negative hydraulic conductivity times area multiplied by the gradients in head. Where head is defined as the elevation of the water table Z for an unconfined aquifer. And head is equal to the Z plus pressure over gamma when we're dealing with a confined aquifer. And the way we might think about Darcy's law is if we have some aquifer that has some thickness to it, that's the bottom of the aquifer. Here's the ground surface. Here's our water table. Sorry, it's hard to draw straight lines here. And if we look at the slope of that water table for an unconfined aquifer, we put a well in here and we get the depth, or we could also think about it as the elevation from the bottom of something, some arbitrary elevation. Say this is H1 and H2. And then this is our length. Then in this case, our gradient is going to be delta H over L. Right. Well, the delta H would be negative. Yeah. Yeah.
Hey, Joel.
Yeah.
So is permeability like lowercase k and then conductivity uppercase k?
Correct.
Okay.
Yeah, and I don't think we're going to be calculating permeability directly. I just want you to know that conductivity is a function of the permeability and the properties of the fluid. And I should note that the units for conductivity is length per time. Okay, so let's talk about transmissivity, and we'll do an example calculation. All right, so let's talk first, let's look at a little slice of an aquifer. This is kind of like a piece of cake right here. And trust me, transmissivity is a piece of cake, but we'll look at a piece of cake. So this is the bottom of our aquifer. This would be like an aquitard bedrock, some impermeable layer. We have the water table in there. This is an unconfined aquifer, right? Let's actually put a bound here and give it an actual width. B is going to denote the thickness of the aquifer up to the water table. And then for transmissivity, we're interested in kind of how much water is flowing through a unit area of this aquifer. T is equal to the big K times little b in this case. It has units of length squared per time. And so W is really just a unit width. We'll get at that in a second. Big K. Hydraulic conductivity. And we might just assume based on the qualities of the aquifer, we can say K is equal to some value. In this case, we'll just say it's 50 meters per day. We'll go back to the Darcy's equation. Q is equal to negative big K times area times the hydraulic gradient. A is equal to B times W. So I'm just substituting BW in for A right here. And then because transmissivity is equal to K times B, then we can say this is equal to negative T times W times DH over DL. So ultimately, we can calculate transmissivity as a property of all these parameters. So if we solve for T in this case, we can get T is equal to the discharge per unit width, so Q divided by W, times the hydraulic gradient, the inverse of the hydraulic gradient, DL over DH. And so this is the kind of formal definition. This is how you might calculate the transmissivity of an aquifer. Are we still recording? Okay.
Yeah, you're good now.
Okay, great. What does transmissivity tell us about an aquifer? Yeah, how much flow is moving through it? How much water you can kind of move through this aquifer? It's going to be a function of the hydraulic gradient. We can make some measurements or make some determinations of discharge in an aquifer, and actually get an idea of how much water is flowing through an aquifer. Let's do a calculation. Yeah.
Does B depend on assuming B is large compared to like how much it drops to a minor distance?
Yeah, so you're assuming B doesn't change over time. Yeah, that's an important assumption. I guess a couple other, yeah, let's talk about assumptions. I skipped those. Engineering problem solving, right? All right, so assumptions, this is steady state, meaning the discharge isn't changing over time. And then B is large, meaning it's not changing a lot over time or over space. Let's calculate, let's do an example. We're going to calculate T and K. So we'll look for this example. We'll have some idealized aquifer and unconfined aquifer. And we've got kind of a valley going down to a creek or a stream. It comes back out. And we've got a well that goes down and where you can observe the depth of the water. We'll say it goes all the way down. And the flow path for this water, this groundwater is, it's kind of going downhill towards the creek, right? This creek also kind of goes back into space, so it's got a length associated with it. And we'll say that, here, we'll kind of run it over here. We've got 2 observation points where we're measuring discharge. And between those points, we have 5,000 meters. The thickness of the aquifer is 50 meters. And then from the well to the water surface, let me just, let's just draw it down here. Just getting a little cluttered. The length is 2,000 meters. Our DH is 1 meter. So you can imagine a situation where we've got a creek. We can measure the stream flow through that creek over a valley that has like a homogeneous type of aquifer material in it. And we can take observations of the discharge change under base flow conditions, so no surface runoff between these 2 points. And then we can have an observation well nearby and try to get an estimate of the hydraulic gradient between of the water flowing from the valley margins to the creek or the stream. All right, so we have 2 stream gauges, and at point 1, we have measured 2.355 cubic meters per second. And at the second stream gauge, we've measured 2.485 cubic meters per second. All right, so we got a little bit of an increase, right? And our delta Q in this case, we just do the subtraction or the difference there, we got 0.130 cubic meters per second. That's our delta Q. And that's over that 5,000 meters, right? So first we're going to assume we're under base conditions. Yeah. What's up?
What's DH real quick? What's DH?
So DH is
I know it's 1 meter, but like.
Yeah, so it's the change in elevation. I didn't draw it super well here. It's the change in elevation from this observation well to the water surface in the creek. Does that make sense? It's the gradient, it's the overall slope of the water table from that observation well to the creek.
Okay. Okay, makes sense. Thanks.
Yeah. All right, so what we're going to do to solve this problem is we're going to basically cut this problem in half, because we have water flowing from this side and we have water flowing from this side. And we're going to assume that the water's flowing at an equal rate. So the first thing we'll do is we'll find the inflow to the stream from groundwater between points 1 and 2. And then we're going to divide by 2, because we're going to assume that we have equal contributions from either side of the valley, or either side of the stream. Then we'll convert to cubic meters per day. This is the kind of the units of K. If we did it per second, it's going to be a really teeny tiny number. So let's go ahead and convert the cubic meters per second. So we want to divide this by 2, remember? So convert to cubic meters per day. Yeah. And then we'll go back to that transmissivity equation. right, so have you guys do that conversion, and I'll write it out here slowly. So we have 0.065, is that right? So 0.065 meters cubed per second times 86,400 seconds per day is equal to
I got 5,616.
5,616 cubic meters per day. Thank you, Edgar. All right. Now we'll go back to our equation for transmissivity. T is equal to the unit discharge, the discharge per unit width. In this case, we know the discharge that's coming in over that 5,000 meters times the inverse of the hydraulic gradient, dl over dh. And so all we'll do is plug in those numbers, 5616 meters cubed per day. And that's going to be divided by 5,000 meters, which is our W. And then we'll multiply that by our DL over DH. Our DL was 2,000 meters, and our DH was 1 meter. So we end up with meters squared per day, which is the units length squared per time of transmissivity. And if we do that calculation, we get T is equal to 2,246 meters squared per day. And then we said T is equal to K times B. And K is going to be equal to T over B. Divided by our aquifer depth, which was 50 meters. And that gives us a hydraulic conductivity of 45 meters per day. So this is actually something you could do. You could measure flow rate. Flow rate is hard to measure in surface water. It's hard to really measure anywhere. So you have to have a really precise way of doing that. And the best tool we have these days is called acoustic Doppler profilers. And they're able to give you, usually they're boat mounted or even a raft mounted. And they're able to basically tell you the velocity of these cells in the river over the 2 dimensions of that cross section. And they give us the most accurate estimation of discharge. So we could use some really precise instrumentation to do that. You could have a flume upstream and downstream. Sometimes in research areas, we use flumes to get that difference in discharge. And then you could have observation wells, and then you would get this transmissivity and hydraulic conductivity.
Structure like a lower dam, would that be good?
We used weirs. You can use weirs, right, to calculate discharge. A dam like that, certainly, you could come up with a weir coefficient for it. So yeah, really any kind of hydraulic control can be used to get a better representation of discharge. All right, that is our first calculation. We're 30 minutes in. And I think I'm going to do one more, and then we'll take a quick little brain break.
What do they use to split the water between upper and lower phase? Like measure that?
The stream gauge?
Yeah.
So the way a stream gauge works is,
a stream gauge that they use?
yeah. Do you know how that works? Okay, we'll just We'll do a stream gauge real quick.
Hey, Joel, really quick.
Yeah,
That last example, that was a confined.
unconfined,
It's like confined, the one where it's like pressurized.
not pressurized.
Not pressurized.
Yeah, not pressurized. Yeah, let me assume base flow conditions, and then yeah, and what if we do have a confined aquifer, we would draw that confining layer, so it'd be really obvious. In this case, you can see that this water table surface, I draw that little triangle. That means it's a free surface. There's no pressure acting other than atmospheric pressure on that surface. Thanks for that clarification. Real quickly about stream gauges. The way stream gauges work is they measure something that's easy to measure. Here's a little stream gauge house. Maybe it's like a corrugated metal pipe and they put some data logger in it. And what they're usually measuring is, well, I guess we'll just do it the most simple way. There's a lot of different ways they can measure the stage of the water. The kind of most intuitive way, I think, is just an acoustic sensor, like a Doppler kind of thing. Not, what is it? Anyway, it sends a ping down, and then a ping comes back, and it's able to tell you the distance of that water, the elevation of the water, relative to some datum. So they'll have some surveyed benchmark. And so it's going to be, this surveyed benchmark has a certain elevation associated with it. And then we can get the elevation of the water relative to that datum. What they do, so this is easy to measure, and we can measure that every 15 minutes or something like that, right? Just the elevation of the water, the stage.
That tells you a flow because you have a cross-sectional area at that point.
So the way you get to flow is you basically are just doing a statistical relationship, an empirical relationship between stage and discharge. And so typically for a rating curve, we put stage on the y-axis. But in linear regression, stage is going to be our independent variable and discharge is the dependent variable, the one we want to try to predict. Usually that goes on the y-axis, but this is the way we visualize rating curves. So you have to develop a rating curve, and each USGS gauge has a rating curve that's developed from point measurements where they'll go out in a little boats, or maybe they have sometimes you'll see these tramways that kind of go across a little cable car, and then they'll sit in that cable car and they'll put down a device that can measure the velocity of the water. Or they'll get in a boat and put their acoustic Doppler velocimeter in there and just go back and forth, right? And so they take velocity measurements across the channel. They know the depth of the water because they know the cross-section shape, or maybe they measure the cross-section shape every year or something like that because it's going to change. And so if you add up all these velocities and areas, you get the discharge, right? And so each time they go out there, and they'll go out there, many times a year, there's a whole host of hydrologic technicians that go to all the USGS gauges and they take their measurements. And so they get a bunch of points. Over time, and they fit a curve, which is just an equation. Q is equal to some function of stage. And that's a rating curve. That rating curve is always being updated. They're always, they're going out and taking their measurements, and all of a sudden, if they get a couple of points over here, they're like, oh, we got to shift the rating curve. And they document all that stuff. So you can go to any USGS gauge and download the rating curve. It's data that they have up there, and they also document every time they go out and take a measurement. It's really hard to do in natural channels. It's hard to do well. That's why you have to have really sophisticated equipment, and the USGS has, the best equipment, basically. Yeah. All right, let's do one more setup here, and then we'll take a little brain break. We're going to talk about Dupuis equation. Again, sorry for the butchering. And again, this is for steady state flow. And really, this is just another way of writing Darcy's equation, but we'll kind of, but it's how we think about how we might actually measure hydraulic conductivity or groundwater flow based on observations from two different wells. So here's our ground surface. We'll have one well, then we'll have another well. I have our water table, and the water table is going to be sloped like this. It's unconfined. Right now it's unconfined, but this works with confined. This is unconfined. And water is flowing in this direction. All right, so let's just list out the assumptions here. So one is we have a free surface water table. Which really just means it's unconfined. We have a very small slope, or hydraulic gradient. This is kind of similar to when we did open channel hydraulics, and we said that the gradients is small enough that things are transitioning smoothly over time. We don't get like turbulence or bending flow lines and that sort of thing. So this also means that the streamlines are parallel. Streamlines are parallel to each other. So streamlines are just if you were to put like a dye in the water, that dye would slowly make its way in a parallel fashion with any other point of dye that you would introduce into the aquifer. So they're parallel to the water surface. And that's streamlines are symbolized by the symbol psi. And then equipotential lines symbolized by phi are perpendicular. And so if these lines right here are psi, then this would be an equipotential line. All right, and then the last assumption here is that the friction slope, the friction slope is equal to the actual slope of the water. So this is uniform flow, and we saw this in open channel hydraulics. This would be the slope of the hydraulic grade line, and this is the slope of the water surface. The hydraulic grade line is just it's going to be equal to the water surface for an unconfined aquifer. All right, if we, so we're looking at this aquifer, kind of a two-dimensional slice. Now the aquifer, we could imagine, extends out into space at some unit width. We're not going to define what that is, but we're going to put this equation in terms of Q over W is equal to lowercase q, which is just discharge per unit width of aquifer, per unit chunk of aquifer. And we'll go back to our Darcy equation and say that this is, actually, we'll first need to define a couple things. The height of the water table above some aquitard or some impermeable layer at this point is going to be h naught. So this is going to be 0. And the x direction is in this direction. And then the height of the water table at some point downstream is going to be hx, h as a function of x. All right, so back to our Darcy's equation. For when we do the lowercase q here per unit width, we write it as k times h dh over dx, where it used to be area here, but we divided by w. So the depth of the water table times the width of the aquifer would be area, right? So we just took that w out. So h is just the depth of the water table. So there's a derivation here, and I'll post my version of it on Canvas. It's also in your book, but we're going to skip the derivation, and we're going to say that based on 2 observations of the water surface depth from one point to another at some distance L, so 2 observations of water table at distance L, then the discharge can be related to those observations and the hydraulic conductivity. So K over 2L times H naught squared minus HL squared. In this case, X is equal to L. So just some distance between this observation and that observation. So what this does is this describes the water table surface as a parabola. And this ultimately is what's going to lead us to the cone of depression calculations that are kind of the bread and butter of FE level groundwater hydraulics. There we go. Val and Edgar, you guys on? Okay. Hopefully that's a yes.
I am, but I don't
Okay.
see Edgar.
We lost Edgar. Okay. Well, I'm recording it, so you can look at this. We have, so we'll just we're drawing a lot of these cross sections here. So this is first we'll do an unconfined aquifer. and we'll have a well coming down. So in this well, we're pumping water out of the well. So we've got a pump, and there is a flow rate, big Q, coming out of it. And we're pumping so much water that we're getting a cone of depression. Now, this, of course, is really exaggerated, right? We talked about the slope of the water surface not being very great. So we draw this in a very exaggerated manner. This might be, you know, a drop of a foot over thousands of feet or something like that. All right, and then we can have another well, and that could be a well nearby, or it could also be just a well. We could be doing this calculation between two wells. These would just be two observation wells, right? The pumping is happening over here, and then we have two observation wells. You just need two wells, either the well itself where the pumping is occurring, or two wells nearby, so you can get that slope of the water surface. All right, we're going to define a bunch of things here. This would be the original water surface, is that dashed line.
It's like what my roommate does for work, cleaning free product off the top of water table.
Gross. Like what, like from gas stations or what? Oh, I had to do, that was my first job, was environmental stuff. There's some gross stuff out there.
Yeah.
Ugh, diesel spill, and just like, it smells so nasty. Okay, and then we're going to define this as some distance r. Sorry, let me do this. The distances are going to be between the center line of the wells. Okay, so the center line of this well and the center line of this well. The well diameter can actually make a difference, or the well radius. So in this case, this is the radius of the well. And then we can have the water table height at some distance, some r distance away from the well that's being pumped. And then we can have the original water table height, or the initial water table height before pumping began, which is h naught. And then we have the water surface slope, which is dh over dr. So let's take a look inside the well itself. We have that radius of the well. We have the water depth in that well. And we can define the area that the water is being pumped. And so the area is really just going to be this cylindrical area, right? The area that the water is being pumped out of that well is 2 pi RW. So that's going to be the circumference times the depth. So just length times height. So that's the cross-sectional area that we're pumping water out of. And if we go back to Darcy's equation, we know that Q is equal to negative K times area times the hydraulic gradient, in this case dH over dr. And so we can say that that's going to be equal to negative 2 pi RW HW times K times dH over dr. All right, and then ultimately to solve this equation, we have to integrate it because we want to get rid of this differential here so that we can integrate the equation and solve for Q and basically solve for this linear surface as well, based as a function of Q. So if we know Q and we know K, then we can calculate, if we integrate this equation, H as a function of R, vice versa. So we'll do some integration, and then we'll end up with this cone of depression equation, which says Q is equal to pi times K, H minus HW squared all over the natural log of R over RW. So integration gives us this, where we have HW is at the well and RW is at the well. And this is some distance R, right? And this is at R. And so you can define that water surface elevation H. Ultimately, you're solving for H, right? If you want to define that water surface cone as a function of distance R and Q. Alternatively, you can say, given I'm pumping, say I'm pumping out 100 gallons per minute or something like that, right? Then I have my two observation wells. I could tell you what the H is going to be in this well and what the H is going to be somewhere else at some radial distance away from that well, given this discharge rate, given the pumping rate. So this is when you have an observation at the well and then some distance away from the well, or you could base this off of just two different observational wells. And that's just going to be a very similar equation, which is pi k H2 squared minus H1 squared all over ln of R2 over R1. In which case, this could be well 2 and this would be well 1.
They usually do this in terms of like relative to the well or elevation.
It's defined, what you measure is the depth from the well casing top, right? So you put a little tape down there and then it hits the water and it beeps, and then you read off the depth to the well. So you can set H as some arbitrary datum. You could say, okay, my aquifer is going to be 100 meters deep, and then you just subtract what you measured from that. So it's all in terms of H. You could rewrite that in terms of depth to the well, but we put it as H.
How do they determine the actual depth of an aquifer? And if you poke through it, all of a sudden it's coming up.
Yeah, a well log and a really deep well.
Yeah.
And you're like, okay, clay, 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 sand, 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 gravel, 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 sand, 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 clay, 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 and then you're like, okay, that's my bottom. Yeah, that would be the way to do it. All right, let's look at a confined aquifer setting. It's going to be very similar, just a little bit different. And we'll draw our confined aquifer. I'm going to draw kind of a big picture confined aquifer. So we'll have the ground, we'll kind of start up in the mountains and we'll come down to the plain. So this will be our ground surface. We'll have some sort of aquitard. I'm going to make it red. So that's our aquitard. And then this would be another aquitard at the bottom of that. So here's our aquifer, our confined aquifer. And somewhere up here, we have a water table that has a free surface. But as we go down here, it starts to be pressurized, right? We get those Artesian conditions. So there's a potentiometric surface that, you know, essentially, let's see, I'll just kind of draw it like this.
What's the difference between them two?
Just a sec. Say that again.
What's the difference between the two aquifers?
So this would be, you always, for confined aquifer, you always need to have a sandwich. So you have one aquitard and another. So this sandwich is where the confined aquifer is in. This is where the pressure builds up.
Oh,
This kind of acts like your pipe walls. So the aquifer is here and the water is moving down this way. And you've got that potentiometric surface, which is basically the pressure that exists. And if you were to put an observation well in here, the water would rise up to this potentiometric surface. So if we put some wells in here, I'm just going to do 2 wells this time. And we start pumping. Instead of a cone of depression from the water table, we get depression in the potentiometric surface, which manifests as the free surface in a well. So it's really just like an imaginary cone of depression. So wherever you put that well in, the water's only going to rise so far based on that cone of depression. And if we're pumping out at a certain flow rate out of that well, we can do, let me just define this as potentiometric surface. And we'll do some similar calculations here, but we'll introduce a new parameter. In this case, we have the thickness of this aquifer, the confined aquifer, which is B. We'll have the height of the water in the well. We'll have the height of the water somewhere else. We'll just call that H sub R. And then we'll have a radius between the 2 well center lines. And then in this case, our cone of depression equation, Q is equal to 2 pi B times K, H minus HW, so they're not squared this time, ln of R over RW. Alternatively, if we had 2 wells, this would be Q is equal to 2 pi BK, H2 minus H1, all over ln R1 over, sorry, R2 over R1. All right, so this is the kind of classic FE groundwater kind of question. So that's why we're doing it. And it gives you kind of a basic idea of steady state flow. And the way this would work is we set up a well, you start pumping, and you're pumping at a constant flow rate. And so there's 2 questions we could ask, or 2 kinds of problems we could solve. So the first problem would be, given that pump rate Q, which is steady, let's calculate the drop in well elevation or groundwater elevation at some distance. So this is like a drawdown, you know, how much am I going to impact my neighbor's well Or am I going to create a reverse gradient so that all of a sudden water is starting to flow from a certain area that where it didn't before? Because you can kind of reverse directions of groundwater flow. We talked about that example on Tuesday where you could potentially be drawing water from a surface source that you didn't want to go into your well. The other thing we could do is we could say given Q H1, H2, what is K? So we can actually calculate the hydraulic conductivity based on this steady state. And so steady state is where we turn the well on, we pump at a constant flow rate for days, right? Maybe even weeks, depending on the hydraulic conductivity of the aquifer. If it's a really low hydraulic conductivity, it might take days, weeks, months to reach a steady state where that groundwater is not drawing down slowly over time, increasing the slope. If it's a really low hydraulic conductivity like sand and gravel, it might take days. However, sometimes we don't have days to pump and test things. So we might need to use unsteady equations and unsteady relationships to measure properties of the aquifer based on hours long test or a day long test or something like that. And that's called pump testing and slug testing. We'll talk about that in class on Tuesday. And also do an example because we ran out of time. So I'll do an example on Tuesday of this, and then we'll talk about slug testing and pump testing. Basically aquifer testing. All right, so I will be available for office hours on Zoom tomorrow from 10:30 to 11:30. If you need to talk to me outside of those times, just email me. We can set something up. I'll give you your exams back. And Edgar and Val, I can scan yours and send it to you, if that works.
Yeah, that's fine.
Jake's got his. I can also hang around if you guys have any questions here. And Val and Edgar, I'll scan yours and send it to you in the next few minutes.
See you guys on Zoom.